Module 5, using the machine learning core. In this module, we will learn how to configure the machine learning core using the STMicro tool, and use this configuration to run the MLC on the STWIN board. We will then visualize the MLC output with Python scripts. Close any windows you may have opened from the previous module. We will be using the STMicro application to create our sensor configuration file. Unico is a software application developed by ST to evaluate the MEMS sensors in ST's portfolio. It can communicate with ST sensors and test the performance under various scenarios. It can also be used to generate advanced configurations for features such as the machine learning core and the finite state machine embedded within certain ST MEMS devices. Let's start by opening the Unico application. In the text box to the right of the magnifying glass, type SM330DHCX. Select any of the two ST-eval boards that are populated in the box below. Uncheck the communication with the motherboard box and then click on the Select Device button. Unico will pop up a warning notification. This is normal for our STWIN setup, and you can click OK here. Select MLC of the menu bar on the left. We will be loading our shake and no shake data captures using this screen. Click on Browse. Navigate to the C:\\STWIN workshop directory. Open the STWIN no shake Unico folder. Select the SM330DHCX text file and click on Open. The no-shake data pattern will be loaded into the current data pattern section. Set the label to no shake and click the Load button. If you receive a larger sample set warning, just click OK. The pattern will now be placed into the Data Patterns Loaded section. We will repeat the same process for the shake data captures. Click on Browse. Navigate to the C:\\STWIN workshop directory. Open the STWIN shake Unico folder. Select the SM330DHCX text file and click on Open. Set the label to shake and click the Load button. If you receive a larger sample set warning, just click OK. The pattern will now be placed into the Data Patterns Loaded section. Now click on the Configuration tab up top. Make sure the device box is set to SM330DHCX and click Next. Set the MLC ODR to 26 Hz and click Next. Set the inputs to accelerometer only. The accelerometer full scale should be set to 16G and the ODR to 104 Hz. Click on Next. We are only deciding between a shake and no shake event, so set the number of decision trees to 1 and click Next. The window length is the number of samples used to compute the features of motion for the particular sequence of sensor values we are attempting to classify. Since the motion we are classifying is not very complex and does not have many steps, a window length of 26 is sufficient. Set the window length to 26 and click Next. In our use case, we are not configuring any of the built-in filter logic of the MLC. Set the filter configuration to End Filters Configuration and click Next. Under the Features section, scroll down to Feature Peak to Peak. Since a no shake can be determined by low motion, while a shake can be determined by strong peaks and troughs in our data, the feature we are using to classify the motion is the peak-to-peak acceleration vector squared. We square this value because the directionality does not matter, only the amplitude will be taken into account. Click the enabled checkbox for the ACCV2 input. Click on Next to continue. We will now save these selected inputs to an ARFF file, which is an MLC model compatible file format. Click on Browse. Navigate to the workshop directory. Set the file name to MLC and then click on Save. Click on Next and wait for the file to be saved. Once the progress bar completes, we will set the decision tree result values. We will keep no shake and shake at their defaults, but these can be set to any discrete numbers if you choose. Set the no shake value to 0 and the shake value of 4. Click on Next. We use the number of nodes to minimize the size of the MLC as much as possible. We will only use one node in our decision tree since the motion we are classifying is relatively simple. If we were classifying more complex motion, we would increase the number of decision nodes to increase the accuracy of detection. In the decision tree file section, set the max number of nodes to 1. The confidence factor controls how much of the decision tree is pruned. A high confidence factor ensures that more values within our training dataset are classified correctly. Set the confidence factor to 0.9. Set the decision tree name to DT1 and click on Generate. The decision tree file will now be saved to our workshop folder. The info section shows the specific details of this newly created decision tree file. Click on Next to continue. The meta classifier is an additional filter on the output of our decision tree. It will count how many of a particular event is detected prior to changing the state of the MLC. In our use case, we are not too concerned with accuracy, so we will set the meta classifier value to 0. The MLC output will change as soon as an event is detected. Click Next. When the Save Configuration File section appears, click on Browse. Navigate to our workshop directory. Name the file as MLC and click on Save. Click on Next to save the configuration file. A pop-up window will notify you once the file has been saved. Click on OK. You can now exit the Unico application. We will now edit our device configuration file again. Open a File Explorer window and navigate to the bin directory in our Data Log Utilities folder. We will update the sensor status settings for the 330DHCXMLC. Open the device config file for editing with Notepad++. Scroll to line 450. We need to keep the ODR at 0 for the output to function properly. Set the Is Active parameter to true on line 455. Set the Use CF Loaded parameter to true on line 461. Save the file and exit. Type CMD in the File Explorer path bar to open a command prompt window. We will now initiate a data capture and shake the board vigorously to trigger a state change in the machine learning core output. Enter the following command, but do not press enter until you are ready to shake the board. CLI example-f device config JSON -t 60-uc:/STWIN workshop /mlc.ucf. A -u parameter specifies the location of our Unico MLC configuration file that we just created. You will alternate between shaking the board for 5 seconds and keeping it still for 5 seconds. This should result in the MLC1 status changing between 0 and 4. If you see random data in any of the other MLC status values, simply give the board a quick shake to reinitialize the CLI application. Press Enter to execute the command and then press Enter again to start the logging process. Keep the board still for 5 seconds. The MLC1 status should be at 0. Now shake the board for 5 seconds. The MLC1 status should change to 4. Repeat this process until time runs out. We will now wait for the capture application to complete and then close the command prompt window. This completion process can take 10 to 30 seconds as the captured data is saved on our PC. You can now close the command prompt window. In the File Explorer window, you should have a newly created capture folder. This folder contains the MLC shake data we just captured. Rename the folder to STWIN MLC and move it to our workshop directory. Let's navigate to the Python SDK directory and then type cmd in the File Explorer path bar. Type the following in the command prompt window. Python hs datalog plot.py c : /stwin workshop /stwin mlc. Press 0 to plot the ISM330DHCXMLC data. 2 plots will be displayed. The accelerometer plot shows the disruptions in acceleration due to shaking the board. The MLC plot shows the machine learning core state changes from 0 to 4, where 0 represents no shaking and 4 represents shaking. These state changes should correlate to the acceleration shake events but may lag a bit while the MLC obtains enough data points to confirm the presence of an event. You can close the plot windows once you are done reviewing them. Close the Command Prompt and File Explorer windows when completed. In this module, we use the STMicroelectronics application to set up our machine learning core. We generated a configuration file for the STWIN board and then generated shake events to trigger the MLC state machine. Finally, we visualized the MLC output using Python plotting scripts. This concludes Module 5.